Welcome to Cookie's Maths and Science Hub. Today we'll be exploring the concepts of scientific notation and significant figures. Scientific notation is a way we can represent really big or really small numbers. It becomes very important in science and in fields of mathematics, as when we start to deal with really large numbers, we don't want to have to write out all those zeros and different parts of that number all the time. So we simplify them using scientific notation. A number is written in scientific notation when a number between 1 and 10 is multiplied by a power of 10. On the right hand side here, you can see how we can use this for simple hundreds and thousands numbers. So when we have 10, we have 10 to the 1 obviously. 100 is 10 to the 2. Remembering when it has that index or indice, it just means, so 10 to the squared or 10 to the 2 is just 10 times 10, which is 100. You can see how we can use this to get into those bigger factors. So we can go all the way up to a million, and well and truly beyond that, we can go up to 10 to the power of 18, 20, etc. And we can go downwards as well into decimals. When we go into those decimals, it becomes a negative power, because 10 to the negative 1 is the same as 1 over 10. So that just becomes 0.1. All it is shifting that 1 into a different unit value. So you can see we start with 10 to the 0. When we have 10 to the 1, it goes up to the left, so it becomes 10. When we have 10 to the negative 1, it moves that 1 to the right, becoming 0.1. Now, of course, these different units have proper names as well. Obviously, we know that when we have 1 followed by 6 zeros, we have 1 million. Now, in scientific notation, we represent that as 10 to the 6. However, we also sometimes use prefixes for these, such as mega or kilo. Kilo is the one that I really want to focus on for this example. We know that kilograms or kilometers, let's go with kilometers as our example. So we know that 1,000 meters is 1 kilometer or 1 kilometer. So we know that that would be 1 times 10 to the 3 meters, because that means we have 1,000 meters. You'll start to see that these are all things we already use in everyday life and know. It's just a matter of applying them and seeing how the mathematics behind them works. Same for grams. We know 1,000 grams is 1 kilogram. The reason we say 1 kilogram is because that represents 10 to the 3. So 1 times 10 to the 3, which is 1,000 grams. It's all about just using these names and different codes to represent these numbers of different sizes. We can use these concepts to begin to explore what's called significant figures. When solving such problems in maths and science with these big and large numbers, as well as really small numbers, sometimes there's lots of different complex parts because of all the numbers that are present. So we want to try and simplify them down. We simplify these down for a multitude of reasons, such as a good example is when you look at a set of scales. A set of scales might only weigh something to a certain amount of decimal points. This means it only gives us that amount of significant figures. Something might weigh 1.46649628 grams. However, if we weigh it on a set of scales, it's only going to tell us those first 3 numbers, meaning to us, that's how many significant figures are there. We need to keep this in mind, as we often only want a certain amount of significant figures when dealing with different properties. On the right here, you can see how we can use scientific notation to shrink the amount of figures that we're using in problems. For example, our second and last example here, and the second last example, you see that we have lots of zeros present, but those aren't significant, as you'll learn in a moment. So we can simplify them down just to have the key parts of understanding that number. Look at the last example, for example. 0.00000000007. That's 7 times 10 to the negative 11, using those ideas of scientific notation. You can see how we've simplified that number and written it in a much more concise form. So, let's look at the rules for significant figures. To start with, all non-zero digits are significant. So if you see a number that's not a 0, it's considered a significant figure in that number. Zeros between non-zero digits are significant. So if we have something like 0.1005, those 2 zeros will be significant. Zeros to the left of the first non-zero digit are not significant, as these only help us locate the decimal point or the unit number that we're working with. For example, 0.00005, only the 5 is significant because we can write it in scientific notation and just ignore those earlier zeros. They're not telling us anything about the number. Trailing zeros, however, they're zeros that are on the right-hand side of any number, are significant because these tell us where the decimal point is in the number. For this reason, it is important to consider when a decimal point is used and to keep the trailing zeros to indicate the actual number of significant figures. Trailing zeros are not significant in numbers without decimal points, such as 56,000, those 3 zeros at the end. Again, can we eliminate them writing scientific notation? Yes, so they're not significant to us. Exact numbers, that is numbers that, go on for ages, have an infinite number of significant digits, but they are generally not reported. Defined numbers also have an infinite number of significant digits. Let's look at this broken down example on the right. So we have 0.004004500. So in this case, that 0 at the start is not significant. It's only there for cosmetic purposes, just to help us look where the decimal point is. The following 2 zeros are not significant because we could eliminate them by writing this number in scientific notation, so they're not significant to us. The 4 is going to be significant because what do we know about non-zero integers? Always significant. Anytime you see a non-zero integer, it is considered a significant number. Our zeros between that 4 and the second 4 are significant because they indicate those values of those 4s. So the 4 and the 5, again, significant because they're not 0. And finally, our trailing zeros, or our zeros on the right-hand side, are significant because it tells us how much that number's been measured to or how far that number goes. When working with significant numbers, you need to be able to identify how many significant numbers are present and also write numbers to less significant numbers or more significant numbers if you're asked to do so. So, looking at that same example again, how many significant numbers do we have? Well, let's have a look. We've got the 4, 4 and 5, so we know straight away non-zero integers are going to be significant. Our 2 zeros are also significant between the 2 4s, and our 2 zeros at the end of the number are also significant. That gives us 1, 2, 3, 4, 5, 6, 7. So we would say this number has 7 significant figures. However, we might be asked to write it to less significant figures. I'm going to go through a few examples using this number now. So, what would this number be to just one significant figure? So you always go to the highest significant figure when you're asked to round or, write them in less significant figures. So in this case, it's going to be that 4 in the thousandths column. So our number to one significant figure is just going to be 0.004. Because we've only been asked to 1, that's all it is. Or you could write that as 4 times 10 to the negative 3, using that scientific notation idea. Okay, what about to 2 significant figures? Well, in this case, we know that those zeros are the next significant ones. So it's just going to be 0.0040, remembering that any trailing zeros are considered significant. That in scientific notation would be 4.0 times 10 to the negative 3. Again, you can see that 0.0 is a trailing zero, meaning it's a significant number in that scenario. What about to 5 significant figures? Well, in this case, we would then have 0.0040045, and we just lose those trailing zeros at the end. Don't forget they are significant, but we've only been asked to signify to 5 significant figures. You could also write that out as 4.0045 times 10 to the negative 3. You'll notice in scientific notation, and I did mention this earlier, we only use numbers from 1 to 10. We never go above 10 when writing scientific notation, because you could write 40 times 10 to the negative 2 and just move that decimal place up 1, but we want to keep it as simple as we can, so we only use the digits from 1 to 9. Below in this table, I've got 4 common numbers. I've got 0.0040607, 467,884 or 467,884, 0.077706, and 54,246. I would like you to pause the video now and have a go yourself at writing these out to 1 significant figure, 2 significant figures, 3 significant figures, and 4 significant figures, in both numerical form and in scientific notation. See how you go. Okay, hopefully you paused the video there and had a bit of an attempt yourself. I've just put the answers up now. Now, going through these quickly, you'll see that it becomes important that you have good rounding skills. And I know that sometimes you don't pick those up in your earlier years and it can be difficult to round with some of these more complex numbers. But you need to be careful when you're rounding that you remember that anything with a value greater than 5 rounds up, or greater than or equal to 5, sorry, rounds up. Anything that's less than 5 rounds down. So let's just look at our second example quickly, 467,884. When I've asked you to write that to one significant figure, some of you might just go, oh, well, it's 4, so I'll just write 400,000, because you've got to remember that then those zeros aren't significant. However, because there's a 6 in the next column, or in the 10,000s column in this case, we need to round that number up to represent what that number is. Because 6 is greater than or equal to 5, so it becomes 500,000 in this case. You'll then notice in our next example, we have 0.077706 to one significant figure. Again, you might just be thinking 0.07, remembering those zeros on the left aren't significant. But because the next number is 7, we need to make sure we round up as well. The last example, 54,246, because it's a 4 in that second column, we do actually want to just keep it at 5 because it's less than 5, that 4 is, in the thousands column. So we round that number down to 50,000 when we just want one significant figure. Now, take your time to look through this and check your answers and see any little tricks that might come up. You'll notice for the scientific notation examples, the power will always remain the same. Because the units are always going to be the same, regardless of how many significant figures you have, the powers will always be the same. For that first example, to the -4, second example, to the power of 5, third example, to the power of -2, and fourth example, to the power of 4. Because where those units are aren't going to change based on the number of significant figures. Only the numbers you have in that actual 5 or 8 or 5 or 4, like what you have before to the times 10 to the power. Thanks for watching. Hopefully now you have a good understanding of scientific notation and how to use it to describe significant figures. Please be sure to like, share, and subscribe to this video, and hopefully we'll see you again soon exploring more of our content.